All right, it's time. Any questions from the homework?
Yeah, can you go over 5.3 number 5?
5.3, number 5. Number 5. Number 5. Integration from this. Gx equals okay. Find g prime x. A complete work should be number 1, figure out what the derivative is if this is x. Okay. Number 2, now rewrite gx to be h, but replace x to be the real ending point. Therefore, g prime is going to be prime of this, which is h prime 5 minus 4x times 5 minus 4x prime by general. Finally, this will be the final answer for number 5. All right. Anton?
Yeah, so kind of going off that in 5.3, number 5, what does t really represent in this equation?
T is just a variable. It's a name of the variable. So the whole thing here is the same as gy equals y 1 x cubed 1 plus x squared dx. So they're really just symbols. You have multiple variables.
Okay.
What we want to say here is actually t is something other than x. That's what we want to say too.
Why can't we switch it from t to x when we're solving for the derivative initially?
We're actually not switching t to x. What we were trying to say is we were trying to say the change in rate of the accumulation equals to the function itself. Okay, so if you do this, let's do several examples to let you see the symbol really doesn't mean anything.
Yeah.
E prime y is going to be y cubed 1 plus y squared. So basically, you're just replacing all the variable here, no matter it's t or x or whatever, by this. What it's trying to say is if you have accumulation, okay, then as x is changing, the changing rate of x will equal to this one here. That's what we're trying to say.
Sweet.
Okay. So you can think of x as the location of where you want to do, because everything here is actually 1 plus t cubed over t squared. But depending on t equals 1, t equals 2, you have different heights, right? So what if I'm looking for the changing rate, which height should I look for? You should look for where your x is, that particular height. Okay. Other questions from the homework? Aaron?
5.4, number 7.
What you're trying to do is you're trying to find antiderivative of this. Okay, so now you have 4 terms. By the property of integral, you can actually split them and do each one separately. So 3 times 1/2 x squared minus 1/3 x cubed minus 3x minus 5 times, do you remember the antiderivative of this? Or you just switch the, that's going to be tangent inverse. Tangent inverse. Okay, so that's actually a formula. All right. Nick?
Could you go over the last problem for the substitution worksheet?
Four. 207. Last one. All right. 11. All right. So for things like this, if I were you, I would try several things, right? What kind of thing can produce this 1 plus x squared? I know, of course. This one can do that. Okay, that's good. That will handle the 2. The problem is, what about some x? Do you know some function that if you take the derivative, not only does it produce 1 plus x squared on the bottom, nothing also produce a x, or maybe a 2x, or maybe a 3x? That is this. And exactly I needed 2. Sounds good? Okay, these are the 2 possibilities that can produce a 1 plus x squared on the bottom. Which one do you need? You need both. Because not only you have an x here, you also have a constant here. And you're not so lucky that these 2 constants just happen to cancel each other. So you need both. All right. With that in mind, what I want to do is I want to take this one. I want to take this one. I want to rewrite it into the 2 things that I know. That is 1 over 1 plus x squared and 2x over 1 plus x squared. Then this one gave me tangent inverse. This one gave me ln 1 plus x squared. Good so far? Of course, they're not just right, because clearly you can see this one gave you 2x plus 1. You want 3x plus 2. Then let's multiply this one by a constant. Let's multiply this one by a constant. So 2 different constants. A times that, B times that. Okay. And I picked the 2 constants, A and B, to be just right, so both of them produce 3x plus 2. Sounds good? Okay. If that will happen, we just need to write the final answer, but with A and B here, plus a C. If the idea is clear, now our job is try to figure out what A and B are. So which 2 number will actually exactly give us 2 plus 3x? That's easy. You want these 2 together produce 2 plus 3x. So you basically want 2a plus 2b produce 2 plus 3x. So your b should be 3/2. Okay, once you finish, you produce a 3x on the top. Your a should be a 2. When you finish, you have a 2 on the top. Together, you have 3x plus 2, which is the original thing. Sounds good? All right, the rest is just try to finish. All right, that's how we handle the last one. It's a little bit tricky. All right. Any other questions? Let's continue. 6.1 basically is over. Okay, we were talking about how to find the area between two curves. We have two possibilities. We can take AB. We can do dx. We use the top minus the bottom. That corresponds to cut everything into this way. And you have small rectangles, vertical rectangles, with delta x and f and the g, and the height is f minus g. Okay? Or we can take the same shape. This time we cut them horizontally. Then for each rectangle, it looks like this. You have a delta y. This one is on the right, this one is on the left, and the real, this time is not a height anymore, it's a width. The wide width is going to be the right minus the left. So be careful, this is dy, you use the right minus the left. Sounds good? Okay, we have two different ways to solve the area problem. Of course, which one is better really depends on what the shape is. Sometimes one is better than the other. Sometimes both of them are bad. Okay, so use your best judgment to try to see which one is better. Worst case, you just do them all. Do both, and you will find you will get stuck with one of them. Then probably try the other one. Okay, that's what we have here. For the area. Now, of course, we go ahead and try to move to volume. Think about what you know about volumes before. You probably know how to do a cube, a rectangular cube. You probably know how to do a cylinder, right? And you know how to do a cone. Do you remember the formula of the cone? It's the cylinder times 1/3. So it's 1/3 of that thing. All right. And maybe some other shapes, but they are all regular. Now what we want to do is we want to push it a little bit. We want to push it to a more general shape. And of course, the tool we have is integration. Okay. Let's start with volume of revolution. That's the first shape we will talk about. What is it? It is basically a shape generated by taking a curve and then rotate it by an axis for 360 degree. Okay, so rotate a curve with, let's just say by an axis for 360 degree. So if you take this curve, what you will receive is, I'll try my best, something like this. It's not anything that we have known before. Okay, it's not even a nice shape. But as long as we assume you know the curve, you know the form of the curve, and you know how much you rotate, you will be able to find the volumes. This is called volume of revolution. Sounds good? Okay. If you look at my bottle, you can see that roughly the majority of the bottle satisfies the volume of revolution, except for the cap. Right, the cap is not symmetric, but well, else you look at it from different perspective, they all look the same. It's basically one curve rotated by an axis. This kind of shape is highly symmetric. It looks nice. Moreover, they have a lot of applications. And the reason is because, where's my Chrome? Oh yeah, because we produce a lot of containers in this way, using ceramic. Here. This is a typical volume of revolution. Has anybody watched The Ghost before? You guys are too young for that, huh? Interesting. For me, that was a classic. And this is the volume of revolution. Okay? Now you believe that we see those kind of things all the time in our life. Don't you think it's amazing that a bunch of apes can figure out how to do this? Like 1 million years ago, or maybe, I don't know, 500,000 years ago. Like they can figure out how to do this. It's so amazing. If you just look at the monkeys, like, I probably won't be surprised to give them another 500 years. They will actually start to take stones or rocks and try to hit people with, hit animals. Okay, with the rock. It's not surprising, but this is amazing. Either way, now I know why we need a volume of revolution. Okay. Now let's try some examples and try to see how we do this. Let's take a simple example. 0, 1, 1. So let's take the part y equals 1 minus x. On the interval 0 to 1, that will be this part. And let's rotate it. By the x-axis. Take this one, rotate. Okay. Can you imagine what the shape is? Can you see it's going to be a cone? By the way, we know the formula of how to do the cone, but let's skip it. We want to do it in the integration way. Okay? So let's think about how do we do this through integration. Remember, integration, when we try to do the areas, we are only familiar with one thing. That is, every time you see some shape, you just cut it into infinite many smaller pieces. Okay? So let's take this. Let's cut it. Why do you want to cut it? Because once you cut them, of course, number one, you can sum them all back together. You got the original volume, original area, whatever. Number two, even though the shape can be weird, but once you cut it, for something like that, you will say more or less it's going to be a rectangle. So a hard shape becomes an easy shape. That's why you want to cut it. Still okay? So before, what do? You take delta x, you take f, you take g, you do this. Okay. Moreover, actually, this comes from the sum from I from 1 to n, the rectangle. If you are looking for areas, that's what you do. Good so far? Now you have a three-dimensional object, and if you cut everything this way, and you have already rotated, you don't just simply cut this shape and receive a rectangle. What you receive actually is going to be something more than a rectangle. It's going to be something like this. Oh, how to draw the last one? Here. Can you see if you have a volume, you cut them in this way, the same way. Instead of rectangle, you're going to receive a disk. Sounds good. Okay. So if you want to do the volume, you simply do the same thing, except this time you do disk. Okay. Then all you need to do is just try to figure out the volume of a disk. Do you know the formula of a disk? Volume of a disk? What is a disk? It's basically a very thin cylinder, right? Do you know the volume of the cylinder? Pi r squared times h. Okay, let's go a little bit further. What is h? H is this. H is very thin. But remember, we have a different name for that. Once we cut things in that, we actually call it delta x, right? That's the rectangle thing. That's our delta x. So instead of h, let's use delta x. Now let's just keep pi r squared here. Good so far? What do you want to do next? After you sum them, you let n goes to infinity. What happened? What will happen is your sum become integral, your delta x become dx, you have your a, you have your b, that's where you start and end, and finally you do pi r squared. That will be the formula for how to find the volume of revolution. But basically, the fundamental concept is you're trying to sum a lot of disks together. Just like the old way, you sum a lot of rectangles together. Anton?
How do you know that the base on the cone is a circle, not like an oval?
If you rotate something for 360 degree,
Oh, okay.
guaranteed, you are going to have a circle.
Yeah.
Right? We will start with this. But later we will say actually the one in the middle, which we call a cross-sectional area, doesn't have to be a circle. It can be a square. For example, think about a pyramid. You take a pyramid, can you cut a pyramid? Of course you can cut it. What are you trying to do? You're just trying to sum a lot of cubes together. You can do it in the same way. Actually, the cross-sectional area can be anything. Okay, but we start with the circle because it's easier. Okay, so my answer to that is if you do the volume of a revolution, then there's a guarantee it's a circle. Good. Okay, so let's try to do this. Let's come back. Okay, now what I'm doing is I'm cutting a lot of disks together. Okay, even though I just draw a line, you should see this line is basically a rectangle, a very thin rectangle. So if you rotate this line, you got a circle, but basically you got a disk. Okay, now what you have is integral, or let's call it sum from 0 to 1, or the disk. The disk has a width, which is dx, delta x, but when you let n goes to infinity, it's dx. All I need to put here is pi r squared, which will be the base area of the circle. Okay, what is your r? It depends, right? Here, r is 0.8. Here, r is 0.1. It actually changes with your location. A different location have a different r, but we're familiar with that. That's just your y. Which changes. Okay, that's why we want to do the integral. Now, the only problem is I cannot do the integral because this is not in terms of x. But can you change it to be in terms of x? Knowing that this one is from here, you just plug it in. That will be the volume of this thing. Basically, what you did is you have a disk. Here's the height of the disk. Here's the base area. Here's the radius. And how did you get the radius? The radius comes from the y value. That's how we did it. Sounds good? Okay. You already know this is a cone. So you take 1/3 pi r squared h. You can always do that. It's going to be 1/3 pi 1 times 1, which is pi over 3. Assuming you know the formula of the cone. Now we're just going to do it in a different way. This is going to be pi. Oh. Integration. You can do this by yourself later. Okay, that's not the focus here. But you can eventually get it. And plug in 1, plug in 0. Plug in 1, you got 0. Plug in 0, you got but then you have a minus here, which give you pi over 3. So we got the right answer. Sounds good? That's pretty neat. Let's try more. This time, let's try some shape which we don't know how to do it. Okay. From 0 to 4. That's going to be a shape. Rotate it with respect to the x. So what's the final shape? It's almost like a headlight of your car. Okay. Do you guys know actually what parabola is used for? The shape? Do you guys know it? It's actually the headlight of your car. You know, I mean, when you do your headlight, right, of your car, you basically have something like that. You put a light bulb here. Okay. Have you wondered what that shape is? Is it half a circle or anything? Actually, it's gonna be a parabola. The reason is because when you put a light bulb here, once you actually start to shoot this one and get reflected, the lights gets reflected, right, from the surface of your headlight. The shape of a parabola will make sure that if you put the light bulb in the right position, all the light coming from the reflection will be parallel to each other. That's why your light can go actually all the way to very far, because of the weird shape with parabola. That's a very special property with parabola. Okay, this part is called the focus of the parabola. Sounds good? So keep in mind, anytime you want to shoot something to a very long distance, okay, you probably want to think about a parabola. For example, radar. Have you wondered what's the shape of the radar? It's always like this, right? And then you have a, I don't know, this one start to rotate. Okay, what's going on here? You basically have a transmitter which can send signals, but you cannot rely on this one to send signals here, here, here. It will be too weak, right? It's not concentrated. Good so far? But what you can do is actually you can rely on all the ones this one sent back to the surface and then got reflected. Once you reflect everything, they become parallel again. So in this way, you can send a signal very, 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 very far away because they're all parallel to each other now. Okay, instead of going like a star shape, going everywhere. So you can actually point that into some direction, which is the direction you want. Okay, either way, that's the parabola. And this is the shape of the volume we're trying to find here. All right. 0, 4. Sum all the disk pi radius is square. Sounds good? What's the radius? From here to here. What is that? That's my y. Okay, but I don't like that. That's my y in terms of x. So I can do it. Sounds good? All right. Zero to 4. Rotated by y equals -1. What's the difference? Before you rotate with respect to the x-axis, right? Now you rotate with respect to y equals 1. Let's still do the rotation. Before, the bottom half should be here. Now the bottom half should be here. Can you see the difference? Basically, you have a whole cylinder filled in the middle. Okay. How do you do it? Same thing. Pi r squared for my disk. What's the radius? Before it was y, right? Because it went all the way from here to here. That's why it's y. Now what's the radius? It go all the way from here to here. Sounds good? What is it? It's just the y and another 1. Because you shift down by 1, right? That's how we do it. Okay? So everything from here to here is y. Everything from here to here is 1. Then what's the radius? Y plus 1. Or you can say y minus 1, if you prefer to use a function difference. Either way. Finally change this to that. Sounds good? Okay, so when you try to rotate it, it doesn't have to be the axis. It can be anything which is horizontal. You can just rotate this way, right? You can even rotate the whole thing with respect to y equals 4. You can rotate by this. Then what you're going to receive is some shape like that. Still integrated from 0 to 4. You have pi r squared. This time your r is going to be this. Right? Then your r is going to be y minus 4. Absolute value. Actually 4 minus y. Because 4 is higher. So you have all the flexibility to pick your radius and the axis of symmetry. So that's all for now. This time let's change a little bit. If you rotate by this, you rotate by this, you rotate by this, you just change the number of radius. Fine. But what if you rotate by this? That's the question. You change the direction. So let's take it from 0 to 4, rotate it by y, no, x equals 4. This time your shape is like that. Right? You still want a disk, right? But the problem, if you still cut things in this way, are you going to have a disk? Not really. You're going to have a, it almost looks like a toast, right? You're going to have something almost like a rectangle, but it's not a disk anymore. Sounds good? So in order to get a disk, what should you do? You should instead cut things in this way. Now, because you're rotating like that, and you're cutting horizontally, there's a guarantee you're going to have a disk again. But this time, a horizontal disk, if we could call it. Sounds good? How will that thing change your integration? Sum all the disks together. Disk has pi r squared, and disk has a height. That height is given by delta y, just like before the height was given by delta x, right? But when you do the integration, you just need to change this to be dy. which come from delta y, because now I'm doing things in this direction now. Sounds good? Of course, the starting and ending point should be in terms of y, not x, not from 0 to 4 anymore. It should be from the y value at 0 and the y value at 4. Finally, your r should be in terms of y, so that you can do the integration. Does everything make sense? Let's do it. Four, this is probably 8 now. Okay. Integration dy. Before we went from 0 to 4, if we do dx, now we want to go from 0 to here for our dy. What is that? Well, y equals square root of x when x equals 4. This is 2. So from 0 to 2, because I'm doing this in this way now, bottom up. Okay. Pi r square. What is r? R is this. That's the radius, right? Okay. What is it? It's the distance between 4 and my parabola. Good so far? So that's going to be 4 minus x. This is 4. This is x. 4 minus x will be the red radius I'm looking for. The bigger the x, the smaller the radius. Sounds good? Finally, I don't like this. I should replace it by that, so I can do the integral. X is not wrong. X is actually correct, but I want the same thing represented by y. All right. Does everything make sense here? So let's wrap it up. For volume of revolution, what you do is you take the integration, you do the disk. You have two ways of doing this. One in x, one in y. If you want to do x, you need to take dx for your height. So that means your cylinder, your disk look like that. And if you do dy, that means your disk look like that. Good so far? Okay. So the real difference here is you use dx when you rotate this way. And you use dy when you rotate this way. Can you see that? For disk, like that, your axis has to be like this in order to get a disk. For disk like that, your axis has to be like this. Okay? So the direction of rotation determines dx or dy you should use. It's not a free of choice anymore. Before we can say if you want to do dx, do dx. If you want to do dy when you do areas, right? For this one, it's not a free choice. Okay, if you rotate this way, your cylinder, your disk has to be in this way, then you have to do dx. If you rotate horizontally, you have to do dy. It's not a choice. Okay, so rotation determines which one you take. We call this one rotating vertically, and we call this one rotating horizontally. Okay, Is everything clear? That will be the first one. You will have a lot of exercises in your WebWorkend textbook problem. It's not hard, but this is the first time you see it. And you can already see it's very useful. So you probably want to spend some time to make sure you know how to set it up. Again, in the exam, for things like this, I only require you to set it up. I really don't care if you can do it to the end, because usually you can. Okay, it's just a waste of time. It's beautiful. Do you want to go ahead and try something that you never did by yourself, but you know the answer? The volume of a sphere. How do you find it? Well, now you just need to change it to be a volume of revolution, right? How do you generate a sphere by rotation? You just take this one, which is x squared plus y squared equals r squared, or more precisely, y equals square root of r squared minus x squared, right? Take that one. Rotate with respect to the x-axis. Okay. What's the volume? That's going to be the volume of a sphere once you finish. Good so far? All right. How do you set it up? Negative r to r, pi r squared. My r is my y, dx. My r is this. Okay. Can you do it? Well, it's pretty easy. Pi. This is your y. Your y squared is fantastic because square root and square cancel each other. Pi r squared x minus pi 1/3 x cubed. R negative r. Let's take pi out. R cubed minus pi 1/3 r cubed minus negative r cubed minus pi 1/3 negative r cubed, which is pi r cubed. There's no pi anymore. I factored out them. Okay. Four. Not two. One. Actually, which we already get it. It's 3/2, and another 3/2. Together, it's 3/4. And that is the formula you remembered, right? Now you get it by yourself. It's amazing. It took people 800 years to figure out this formula without calculus. And once you have calculus, it's just an exercise. It's not even worth mentioning. Maybe you can rework everything you know about cylinder later. Cylinder is nothing but a volume of revolution, right? Okay, and you know the formula. Now you can do it by yourself. The volume of a current. How do you know you should times 1/3? Okay, your teacher told you so. I doubt any teacher actually taught you why you should times a 1/3 at the beginning. Okay, it's actually very challenging without calculus, but now with calculus you can easily do it. Sounds good? The 1/3 come from pi r squared. When you take the integration, you have 1/3 r cubed. That's where the 1/3 come from for the current. Amazingly. Beautiful. Are we good here? Let's move on. 10 more minutes. That's good. Let's take an example. All right. Let's take an example of this. Y equals x. Y equals x squared. We take the area enclosed by these two. And we rotate it by the x-axis. You see the area rotated. Okay. What's the shape? It's roughly a weird cup, right? Before, whatever we got, that thing actually is fulfilled in the middle. Now this time we'll have a hole in the middle so we can put things in. So if you rotate this thing, you're going to have something like this. Rotated. I prefer not to draw it. You can imagine what's going to happen. Sounds good? So this one is like a cup. And now if you're looking for the volume, you should not just count the whole volume. You should count actually what's on the wall, because the one in the middle is actually empty. Okay. How do you find the volume? Same analogy. You have this. You want to rotate. I cut you into pieces. Sounds good? Now let's take each piece. Some piece like that. Okay. Now if you rotate it, what's going to happen? This one is actually going to be rotated. What's that shape? It's not a disc. It's a ring. Right? Or washer, whichever way you want to put it. Sounds good? Okay, so I'm going to take this out. I'm going to actually turn it for 90 degrees so I can draw it. It actually gives you some shape look like this. Ho, ho, ho. It's a washer. Okay. If it's a washer, now you know the volume is nothing but sum all the washers together. Okay, instead of disk, you sum all the washers. You just need the formula for the volume of a washer. Do you know the formula for volume of a washer? You don't? Can you figure it out? What do you think? It's the big disk minus the small disk. Right? Okay, so that's gonna be what we have, pi r squared minus pi r squared. What is your big R? The big R is the very outside disk. And what is your small r? The small r is what's inside the small disk. Can you guys see these two are different color? Wow, great. Okay, then it's fine. No. A small r. Okay, so basically the volume is given by pi r squared minus pi r squared. And of course, remember, this will be the thickness. This one has to be there. That way. All right, with that in mind, can you set this up? volume equals from 0 to 1. Okay. Which one is outside? If you rotate this way, the line or the parabola? The line, right? So whoever above will be outside. Whoever below will be inside. So the line and the parabola. I will stop here. Okay. I think I can already write down the formula. We call this the Washer's method. You can vertically stack a lot of washers together. Of course, you can horizontally stack a lot of washers together. So of course we have a different one. Okay, and which one you take really depends on how your rotation works. How can you start to see where the washer is? Sounds good? Okay, we will try some example next time, but I will show you something. I'm going to give you a preview of something exciting. You guys know donuts, right? Have you wondered how big is the volume of the donut? Other than, $2 is better than $1.50. Okay. What is a donut? It's actually a circle rotated. Right? What's the volume? Let's just cut it. Can you see you are actually just summing a lot of washers together for the donuts if you just cut them in the bagel way, not the other way. Okay, the other way is actually how you cut sausage. But if you cut things in this way, you will be able to actually figure it out. Okay, so next time we will do an exercise, we will know the formula for donuts. And what's the difference between donuts and bagel? I'm not from the United States. Okay, it took me 2 years to figure out the difference between a burger and a burger and a sandwich, and I don't even know that's right. For me, they're the same, except for burger is used specifically for beef. That's right? Okay, I still don't know the differences between all the different noodles from Italian. Pepperoni, is that even noodle? I don't know. Totally. Whatever. They have sauce, they have everything. Everything just looks foreign to me. But what's the difference between a bagel and donut? You don't know? If you see one, can you tell them correctly? You will always use the right word.
One is deep fried and one is just baked.
Which one is
So the bagel is
fried?
baked, and then your donuts are deep fried.
That's the difference?
Essentially, yes.
Why don't we just call it donuts fried bagel? What's... Yeah, fried chicken is still chicken, right? You don't give them another name. So donut is fried and bagel is baked. All right, I would take that. I would write it down, actually. Just in case I forget. Donut equals fried bagel. Well, lesson learned. Great. That's all for today.